Welcome everyone to our final session of the DeFi Market Microstructure workshop here at Fields U Toronto. And it's a great pleasure to introduce Yuri Saporito from FGV in Rio de Janeiro, Brazil. He's going to be telling us about the term structure of implied fees in liquidity pools. So let's welcome Yuri.
Thank you. Thanks, Sebastian. Thanks. So I'd like to thank Sebastian, Faisto, Agostino, and Alvaro for the invitation. It's really great to be back in Toronto after so many years. And so this work, it's a working paper, so I'll really welcome all the comments you guys have. Please do ask the questions during the talk. I think it improves the experience. And it's a joint work with a student of mine, Lucas. So he worked at in Rio. It's kind of we don't have much of the finance industry of Brazil anymore. So it's most of it moved to São Paulo, but we still have hedge funds quite a bit, and somehow a lot of crypto companies in various forms, like startups and also trading companies. And Lucas was working in one of those, and the Zixen is one that he opened recently, him and the other fellows from the previous company. And Diogo, is, some of you might know, he's a professor at Florida, and we are working together on this that Lucas started at his master's dissertation. So just to begin, we were looking at the DeFi, I think that's a lot of you guys too, as a place of new questions for finance, right? And this was probably 2021, 2022, a bit. I started looking at DeFi or Bitcoin, let's say, a bit before than that, but for other reasons that are not quite related. But this Uniswap, we were working on some of look at the data and the papers coming up. And then we saw one of a paper that I don't think it was ever published that kind of related the Uniswap V2 with a payoff the Zach presented as well, the square root. And the obvious question that you might ask as a person from App Finance is, okay, you have this new derivative, you can think of that. And what is the relationship of this type of pools or contracts or whatever you might think of it, and the centralized derivative market? So that's what we're going to, that's how it started. And the more complicated part, as maybe will not be clear from the talk because it's already explained, was a way to formulate the question in a proper sense and then connect these two things. And from that, we figured out that it would give us some sort of implied fee. So a kind of expected fee under a risk neutral measure from T to a capital T time horizon. So we had done the work previously all on V2, but we were able to move to V3. It's not that complex in terms of what we're proposing, okay? And I also want to disclose here, I'm not gonna cite works at the slides, but of course it's not all from me here. So there are, and I think you know, it's just because I just finished up the slides like 10 minutes ago, so I didn't have time to really like polish it up with the references. But I'm not claiming to have all the ideas from the slides, just a few of them. So as standard for at least this part of the type of literature, we are going to assume R equals 0. It's not that important. We can change that quite easily. And you can think of, and this is the data you're going to use, Ethereum USDT, the stable coin. So S is the centralized price. Think of Binance. And PT is the reference price, the instantaneous price within the pool. So for the infinitesimal trade, the marginal price. So we are going to start with at least for this part of the literature where we kind of try to relate to the derivative market, assuming that P equals S. We know, and we have seen many talks here that discuss exactly how to exploit or like to break this. At the end, I will show some ideas of even within this, trying to solve this framework, how to change this and what can you do changing this. It's not easy. And for assumption B, we are going to assume that there exists a unique risk neutral measure. You can think that you have option prices, you kind of calibrate a model. We chose one here that I'm going to show, the Bates model. You can choose other models as well. And with this, QE would be the calibrated, like calibrated, would be the measure related to the calibrated parameters of this model. So under this model, because of our assumption here, S is a martingale under Q. So it's calibrated, as I was mentioning, to liquid options in the centralized market. And from the past of quant finance, we would use this like to price exotic derivatives. And here we're going to use to price the market value of the pool. So that's the idea. Okay. So this is just for V3, the P against S. So S being Binance for Ethereum FTT. So it's not the same, but it's close enough. Okay. And so for V3, the pool the liquidity provider provides liquidity, obviously, with L within a price range of PA/PB. So this is the main difference between V2 and V3. For V2, PA would be 0 and PB would be plus infinity. And no problem. Yeah. Okay. For the reserve curve, that's what we have for the V3. Okay. And since we are assuming that E is equals S within the pool, sorry, we can write the pool value, like the market value of the pool, of reserves in the pool, by VT LP, given that we provide the liquidity satisfying this formula here. Okay? So this is the usual formula. It was not derived by us. Okay, it's already well known. And the V2 is the limit when PA 0 and PB goes to infinity. You get the 2L square root that Zach showed us yesterday. Okay. And okay. So with this in mind, here's just the plot. So it's linear, and then you have a concave, the square root part, and then constant. Okay. And so the idea, what we're gonna think of, it's a liquidity provider that enters the pool at time t, okay, and leave at a fixed time capital T. So we give this time horizon to the liquidity provider. And also he chooses PA and PB. So I decided to provide liquidity within this AMM, so Uniswap V3 with PA and PB. So to enter the pool, this is what it costs. The DT equals to G of ST, which was the function we have here. Okay. But at the end of the horizon at time capital T, the position of the liquidity provider will be what? The value of the position that he has in the pool is the market, what they call the market value of the holdings at time T, which is G of ST, plus whatever he collected of fees between small t and capital T. And since he didn't leave the pool earlier and it's not going to leave before, it's going to leave exactly at time t, we will collect this fee. Okay? And a more realistic, and we didn't do this yet, I don't know if I'll be able to do it, or one would be able to do it, is that ideally can consider here a stopping time, and then you stay within the pool up to this stopping time. That would be more interesting question, but also very, like a lot more complicated. But because in some sense the value, this value here, because it's concave, it's kind of decreasing if you think of a stopping problem, but you're also collecting fees, so this kind of has to have to match somehow, or even the fees need to be larger than what you're looking. So here it starts the more different part. So because of this way that we are thinking of the liquidity provider, we can see BTLP as a derivative on S equals P. So by the usual no arbitrage, so it's not a no arbitrage between EMAp and centralized and decentralized, it's just like seeing this as a derivative, we have this unique risk neutral measure. So and we are assuming R equals 0, but you can see that it's not that important. But to enter in this contract, I would pay VTLP. At the maturity of the contract, staying like this, I will get this. So the price of this contract, like a fictitious contract, will have to have this here. Okay. So now we can just expand this as the price of something that I can actually price within the usual framework we have in quant finance, which is the expectation under Q of this payoff G of ST, which is this concave by parts profile I showed, plus something that I cannot compute. I'm not saying, I don't have a formula for gamma of T, capital T, right? I don't know I'm not, to model this, you have to model so many other things, like how many swaps arrive, you have to have all these other structures, okay? So rearranging this, we can get what I call here the implied fee. So it's the expected fee from T to capital T under the risk neutral measure. And this gives us G of ST minus the expectation of this. Okay? Any questions? Simple. So the first thing you can see, and it's not like complicated, is that if G is concave, ST is a Q martingale, okay, if we're assuming R equals 0. So by Jensen's inequality, we get that what I call HTT, which is the derivative price, is less or equal than G of ST. Okay, the kind of the payoff at time T. And then therefore the implied fee, as you would expect, is positive. Okay, and sorry, and this is related somehow with the impermanent loss. So one of the reasons we started looking at this is because the impermanent loss, although it's a quantity that many people look, doesn't seem that interesting in the sense that the strategy that we are comparing to, it's too simple. It's just not doing anything. You know, like you hold this, and then you have the buy and hold strategy, and then you hold, and the concavities. This is it's kind of flipping the question around. So we get a positive fee. So it's what you would think in the impermanent loss, that the fee should be large enough so it compensates the impermanent loss. Here it's similar to this, but we are actually characterizing the fees implied in the option prices somehow. Okay. So ideally, we would like to have this expectation here, right, under the P, because that's how that's actually the average fee that we'll get if you provide liquidity. But actually, I don't know how one would be able to do this without like working the Q measure and then how to translate the Q measure, the P measure, and then we know that this is too complicated and hard to estimate. So this is the model we chose, okay? So to compute this, we specify dynamics for the underlying asset. Here I chose just the what's called the Bates model, the packet volatility jump diffusion. You have a variety of choices here. It doesn't matter much. Okay, and then DZ are correlated processes. We have a jump process in the spot price. This kind of makes sense if you think of crypto. It would make even more sense maybe to add a jump in the volatility, and this wouldn't make it more complicated to price it, to calibrate and then price. Okay, so as I showed, the payoff G in the Uniswap V3 is a combination of what we could see as simpler options in interval. I'll show in a second more precise formula for this. Okay, and within this type of modeling, which is the idea of Heston taken to the next level, you can price using characteristic function and Fourier transform. Okay, and denoting this, we have this type of formula for the V3. You could have similar things for V2, of course. And ABC here, they are functions of tau, x, and v, A, B, C, D, E, actually. And so they are known in quasi-closed form, similar to Heston. And they are actually these expectations here that you can see. So it's just kind of a future price with a digital. Like you have names for those, but and here that we have the square root divided by 2. Okay. So with this hand, we were able to go back to the data, calibrate the model, and plot the expected fee. Okay. So we had daily data for option prices from Deribit from 2019 to May 2023. Annoyingly, the options don't have like very large maturity. They stop at 6 months. So would be honest to look at the implied fees up to 6 months. More than this, it would be kind of extrapolating from the data somehow, the implied volatility. So we could be consistent, but I don't think it would make a lot of sense maybe. And so we are plotting here in the next, the implied fees as a percentage of the money you need to put to enter the contract. Okay. And I'll plot, as I said, up to 6 months. Okay. So these are, so the dotted and the solid lines, they don't relate much to each other here. So just be careful with that. And sorry. And so this is kind of the same day, So you have the same spot price. I have 2 PAs and PB as a percent of the spot price. So 90% and 10% more. And then here a bit larger, the info. Okay. But I'm looking at parameters of various days. Okay. It's kind of changing the parameters of the model, calibrated one, so kind of realistic, but changing various days here. But the asset price is the same. Okay. Like a what if situation. So one thing that we can get from this is that at least for this period and for these parameters, you kind of get more fees, like 10% of the initial, up to 20% at the end, or 35%. If you, for these different days, if you have a shorter price interval. If you have larger ones, you get less. And this here is not 0. I asked Lucas, the student, to look it up. It's small, but it's not 0. Okay. So here is just a different exercise. I change it, so I have 2 calibration days, so it's 2 different days, and changing they gave the same one that most fees for this day. And a real question we want to answer, and I don't know how it's gonna go, is maximizing PA PB once you have this calibrated, at least the implied fee. Okay. And so this is another plot that we did was so these are days from 2021 to 2023 with consecutive returns in the spot that are larger than plus or minus 15%. Okay, so here it's maybe hard to see colors here, the numbers. So here minus 15, and then here plus 25, and this is the variation of the expected fee. Okay, also for 6 months. 6 months fixed. Today I have yesterday. This day, from yesterday to today, the spot price increased some very large amount, and I wanted to see how much the fee has increased. And it kind of behaves kind of randomly here, but related if you have a big move or big move in the spot price upwards or downwards, you see a movement in the same direction but with different magnitude. Okay, so here it's an attempt to drop assumption A. So S might not be equal to P. Okay, and if you do this, you can show, I'm not gonna do the computations here, but you can show that VTLP is ET of G, the same G that we had before, where Z is this process here. In V2, it becomes easier to look, and this kind of comparing S to P in this way. I don't know if this is I will never compare 2 time series to see if they are equal doing this. That's what shows up here, like a half of the square roots of this and the reversed one. And it seems reasonable because of the square root profile that this would be a possible comparison. But that's how it appears. And then we plotted this for the Initiap V2. For V3 would be a bit more complicated because you have to provide the PA and PB. I didn't think much about it. So this is the plot for Z. It's quite close to 1. We saw this in the previous plot that they were like close together, but it's an I find a more interesting plot because it's kind of a mean reverting process. Positive in the actually, I wouldn't say that it's bigger than 1, but it's kind of mostly bigger than 1. And whenever it moves away from 1, it kind of has this very strong mean reverting to 1. Okay, so one way to so you could try to replicate the computations we did with this Z and G. So you have Z, G of ST. This will be the value of the pool, the market value of the pool. This should be equal to this, but this is now Z capital T G of ST plus the expected fees. Having Z or being equal or not equal doesn't affect our definition of the fees from T to capital T. So this here would be this minus this as we had before, but now this, it's not at all clear from just looking if this would be positive. But you can actually take Z out here, divide by ZT, and look at this as a different measure. You're changing measure with respect to Z. Right? Z, if Z is positive, that seems okay assumption. Z0 equals 1. Okay. Expectation of Z under the risk neutral measure to be 1 or having like this martingale property. I don't know. But that's, if you have this, you can change measure here. And then this here needs to be positive again because of Jensen's inequality for a new measure. It doesn't matter the measure, right? Z is positive, so this is positive, so the expected fee is positive. To exploit this in a similar fashion we had before, that means having a model, calibrating, blah, blah, blah. One way of doing is pricing in this Z measure. So you will have to model Z and see how to change the measure in the Q measure for the Bates model or any other model, how this Z would change the measure. So you might propose a model for Z and see how this can impact the new model and then calibrate this new model. So it seems not, I wouldn't say it's doable, but it's an idea out there. Okay, any questions? Yeah.
So I'm just curious about your definition of like new TLP, the price of your synthetic or your fictitious contract. It seems to depend on little t through gamma big T. So you have new capital T depending on the time little t through capital gamma. How's that? So how's your
This here?
Yeah, because that's the sum of that's T, but
Yeah.
gamma little t.
Yeah. So let's go back. Yeah, maybe the notation is not. G actually will depend only on will be this, right? So it depends only on ST, PA, PV. So the V, the value of the pool at time capital T depends on the small t, but just because of the kind of assumption we're making that we are entering the pool at time T, waiting up to capital T and leaving. It's a kind of we are making this as what I want to say is that it's more like you could think of other agents that might do something different than what we are proposing. You see what I mean? But because of we are kind of restricted. Of course, T and capital T doesn't matter like in numbers, right? But what the agent is doing, that matters a lot. That he's not leaving before small t, that he's entering at capital T, that he's entering at small t, and that's what he'll do for the phi. So somehow, yeah, the notation would be much better if this, just one point. So V at small t doesn't have the phi because you're not there to collect the phi. See what I mean? Like this is kind of an agent-based value, like you're looking at as the agent. But I agree with you that at capital T here should be a small t. Yeah, completely agree. Okay. Thanks. So any other questions up to here? We are approaching the end. I think I might be really early. No? It's and okay. So yeah, even more than approaching the end. It is the end. So that's what we've done. So we had this connection between the EMAp or the pool and the option market. Okay. In this setting we calibrated this jump diffusion model, the stochastic volatility one, and kind of related to this, and this gave us we had this when we were discussing, and it kind of gave us just this idea that usually when you find G function in the literature, what we've seen is you assume no fees. That's very common. So the first paper I mentioned, I forgot the name of the author, is this, I think it was a student at Stanford. Like, you guys might know, I just don't remember the name. And yeah. And so it's usually that for some time the assumption common was you have no fees and then you find the profile, and that was the assumption we were working on. You have no fees and then connect the value, the market value of the portfolio and the market value of the portfolio and the derivatives, do the calibration, you kind of related this. But then we started like, okay, but this is interesting, but you're kind of fixing a maturity. What's really happening? What maturity is this of a pool that you don't have a maturity? So the way that we gave sense to this kind of exercise was adding the fees like operating the position you have in the pool. You have it value, and which is the derivative that we are writing, and you have the fees that you're expecting, and it kind of the idea when we thought about looking at an agent that we have this capital T as a fixed horizon, which is kind of arbitrary, but it gives sense to this kind of implied fee. So the future work we are thinking is this optimization of PA and PB to think of the best, at least based on expected fee for a fixed time horizon, what would be the optimal PA and PB, at least numerically, to try to solve this. And that's it. So thank you very much, guys.